All right, so let's talk about the normal distribution. And again, a normal distribution is a type of probability distribution, and one that happens to be reflected in a lot of natural phenomena. It's also something that is really useful in statistics and in a lot of the applications that we're going to be doing throughout the semester. So I'll write out normal distribution here and then discuss a couple of its characteristics. So a normal distribution has three main characteristics. One is that it's symmetrical. Another is that it's bell-shaped. So I'll start out by drawing these two things here. So here we have values of some variable, and over here we have probabilities. And your normal distribution is going to look like this. It's a symmetrical bell shape. As I described on the last couple of slides, what this tells you at a glance, even without knowing what this variable is or what these probabilities are specifically, is that your most likely outcomes are in the middle here, and then it's less likely that you're going to get an outcome that's over here, and it's also less likely that you're going to get an outcome that's over here to the left as well. So the middle is most likely, and the further away you get from that middle, the less likely your outcomes are. So that's what the height of the curve is telling you there. And another characteristic that it has is that the area under the curve equals 1. And you may remember from the last lecture that I said that when you graph a probability distribution, you can always add up the different bars that you have and they'll add up to 1. In this case, we're looking at a probability distribution that applies to a continuous variable. And I'll write that down in a second as well. So a continuous variable is one that can have decimal places in between the numbers. So we're looking at interval and ratio level variables here, and we're looking at variables that can, get really, really, really finely grained in between the numbers. So as an example of height, you could be 60 inches, you could be 60.0001 inches, you could be 60.00002 inches, or so on. There's not really clear defining lines in between those things. So normal distributions are mainly intended for variables that have that quality, where you could fall anywhere along this axis. They also work for variables that have enough numerical categories that they might as well be continuous. So for example, if you're counting up dozens or hundreds of things, the spaces in between the different categories are not that meaningful, so you can essentially treat it as a continuous variable. Not something that you're going to need to do a whole lot with, but that's just to explain what sorts of variables are going to be appearing here. So to get back to my point, last time we said that when you think about the graph of a probability distribution, you can think about the bars in that probability distribution as adding up to 1. With a normal distribution, even though we're looking at a smooth curve here, you can kind of think about it as being made up of many little bars. So the shape that we have here that I drew kind of badly is really just made up of many bars for each of these possible values. So if we were talking about height here, this would be a bar for 60 inches, this would be a bar for 60.000001 inches, 60.000002 inches, and so on. So the key here is that everything under the curve adds up to 1. And when we look at it as a smooth curve here, we can just say that the area, so the total area in this shape under the curve, equals 1. And often that's referred to as probability density, rather than probability itself. But we're just going to say the area under the curve is equal to 1. When I draw out probability distributions, I'll also be drawing out their means and standard deviations. So last time, we also talked about the fact that probability distributions have means and standard deviations. And we saw an example with the binomial distribution, which was the coin flip distribution, where you could find a mean for the probability distribution, which was the mean that you would expect if you were to actually collect data based on that probability distribution. And the standard deviation was the same thing. So it's the probability, the standard deviation that you would expect to see in data based on the probability distribution. In a normal distribution, the mean is always at the center of the graph. So it's at your highest point. It's where the graph is symmetrical, so this side is exactly the same as the other side of the mean. And if you remember from last time, when we talk about the mean for a probability distribution, we call it mu, which is this Greek letter here. It looks kind of like a funny U-M thingy. A probability distribution that's a normal distribution also has a standard deviation. And here I'll usually draw it like this, where I'll show a little arrow saying we're going this far out to the side, and then our standard deviation is going to be called sigma here. And sigma is another Greek letter that is used to refer to standard deviation in probability distributions. So get familiar with this little chart here. This is going to be how I draw up normal distributions as we go on. So we have our bell-shaped curve. It's symmetrical. The middle of the curve is where the mean is, and then the standard deviation tells you how far spread out the curve is. And as another quick example, I'll put some actual numbers to this. Let's say we're talking about the number of thefts that occurs in a large store over the course of a month. And it's a probability distribution. So this says, what's the probability that this number of thefts is going to occur in the store in any given month? And we're going to say that our mean is 65. And our standard deviation is 15. In other words, you would interpret this as, let me write probability here. You would interpret this as showing that in this particular store in any given month, the most likely number of thefts that's going to occur out of the store is 65 thefts. So that's your tallest point. It's less likely that you're going to have way more than 65 thefts, and the further away you get from 65 going in the positive direction, the lower that line is, showing lower probabilities. And the further you go out in the negative direction towards the left, the lower that line is, showing lower probabilities as well. The standard deviation here tells you how spread out your probability distribution is. So you could also imagine a different probability distribution that looks like this. And here, this one's going to have the same mean. So we're saying in this store here, the most likely number of thefts that's going to occur is also 65 thefts. But what you can see is a difference in how spread out the graphs are. And when we talked about standard deviation back in the first unit of the course, we said it shows how spread out the different values are around the mean. And when you look at a graph, it shows how narrow or how fat the graph is. It's the same thing when we're talking about the mean and standard deviation of a probability distribution. So in the case of the normal distribution here, when we have a lower standard deviation of 15 in this first graph here, it shows that most of the probabilities are clumped around the mean. So it's unlikely that you're going to have much more than 65 thefts or much fewer than 65 thefts, because most of our values and most of our area in the graph is centered around 65. For this other graph here with the standard deviation of 30, the graph is a lot flatter. And what this shows is that the probabilities are more spread out. So as you get further away from 65 going in either direction, your probabilities don't drop off quite as quickly. And instead, it's still pretty likely that you'll get something that's far away from 65, even though eventually you do get to the bottom of that bell curve shape. All right, so that's a brief introduction to normal distributions, and I'm going to hop back over to the PowerPoint now.